everyone. So welcome to lecture 2 of the Modern Machine Learning course. In this lecture, we're going to cover probably one of the most fundamental algorithms for training a machine learning model on data, which is linear regression. And this is literally how do you fit a line of best fit to data? How do you find a line of best fit to data? Okay, so before we get into linear regression and linear regression framework, I wanted to discuss a bit about machine learning in general and give some background for some of the notation and the types of problems that we're going to be working with. And so let's begin with some preliminaries. So in this class, what I will always assume is that we're working with some data drawn from some fixed distribution. So in particular, let's consider we have some data, X and Y, which is drawn from some distribution. And here what I'm thinking of as X and Y is X is just going to be these vectors in D dimensions, which is going to represent our samples or feature vectors. And this is kind of like the features or whatever data, like images that you're given to work with. And then, of course, with each one, you have some corresponding label, which I'm going to assume takes some real value for now. And in the case of image classification, if X is an image, Y is going to be a label telling you maybe what object is in the image. Maybe it's some function of the image. And so the whole idea is there's this unknown distribution that we're trying to learn. And the way we're going to learn is we're going to be given a set of n samples drawn from this distribution. So I'm going to call these xi, yi pairs for I equals 1 to n. And I'll always use the variable n to denote number of samples in this course. And so this is going to be some subset of Rd cross R. And this is what I'm going to call my training data. This is my training data. And given this training data, what I want to do is I want to learn some function, f hat, that's a map from Rd to R, such that f hat of x is going to be approximately y for any pair of samples, x and y, drawn from my distribution. That's the goal. And of course, what kind of function is f hat? Maybe I try to restrict it. For now, what I'm going to say is that f hat is contained in this larger class of functions f, where f is the set of all functions from Rd to R in general. And of course, what we're going to do is we're considering right now a very general space. This is super abstract. We're going to want to consider some subset of the space, this curly f here, to where we can actually use some parameterized model and learn something. But okay, so right now there should be many questions in your mind about what exactly is this curly f? How are we going to learn some f hat from this f that fits the data? And importantly, what does this even mean? What does it mean for f hat to be approximately, f hat of x to be approximately y for any pair of samples x and y drawn from this distribution? So these are kind of the core machine learning questions. These are the questions at the heart of machine learning. But before I go and give some concrete answers for these in the context of linear regression, let's just work through some examples to make this abstract notion very, very clear. So the first example I wanted to give is a simple regression problem. And this is going to be housing price prediction. And I believe actually a similar example is given in Andrew Ng's Coursera course. I quite liked it, so I decided to reproduce it to the best of my ability. So in this case, actually, I think this is a Kaggle challenge now too. The goal would be you're given a set of houses and features regarding these houses. So your xi's, so the set of xi's is features describing a house. And this can be number of bedrooms, number of bathrooms, and so on. Square footage, let's say. And then similarly, you have these labels, which are going to be labels of the price of a house. Okay. And the goal here is, given some n training samples, so let's say I have 100, let's say n is 100. So this would mean I have 100 houses where I know the features of the house and the price. Okay, so given this data, your goal is to build a model so that when I have a new house, maybe like the 101st house, I want to be able to predict what is the price of that house just from the features alone. And so that would be the goal here. Of course, there's like high monetary value and stuff like this. And in fact, Zillow even launched this challenge, and they would pay you, I don't know, several $1,000s for getting the best predictor here. Okay, so this is an example of regression. Write that here. This is regression. And the reason it's regression is I'm trying to predict some continuous variable, which is this yi. So these are the prices, which are real values. Okay. So another example would be image classification. And in this case, this is also a very prominent challenge. In fact, it was in our introductory slides because of how powerful deep networks are on this task. But in general, this problem is, given your xi's, these are now images of objects. And typically there will be some pre-existing number of objects. So if you look at data sets like CFAR10, this will involve 10 different objects. And this will be like dogs, cats, birds, trucks, cars, and so on. Okay. And then here, your yi is going to be something called a one-hot vector, describing the class label. So for the case of a dog, let's say, in CFAR10, if dogs are class 1 for me, what I would do is I'd build if I have a dog image, the corresponding label would be a one-hot vector, which is a 1 in the first spot, and then zeros in the remaining 9 spots. And of course, the goal here is, given some finite number of images. So CFAR10, for example, you have n equals 50,000. The goal would be to build a model that can classify these 50,000 images, and then of course generalize to new images. So given a new picture, I want to know whether a dog is in this picture, a cat is in this picture, or whatever. Okay. So these are just 2 examples of that fit into this general framework of learning from training data. Of course, all of this is still quite abstract. I haven't told you how to find any of these functions, and in fact, you should have kind of 3 main questions that I want to frame now that will help us figure out how we want to go about doing this. So 3 questions. Number 1 is going to be, how do we actually measure model performance? And in particular, what I mean by this is, what does it mean when I wrote, what did it mean when I wrote, I want f hat of x is approximately equal to y? In this case, what it would mean in the example of housing price prediction, it means if I'm given a new house and I know its features, I want to be able to somehow reliably predict the price of the house. I want that estimate to be very close to the true price of the house. And how do we actually quantify that? So that's an important first question. The second question is, what class of functions f do we use? So right now we've talked about some class of functions just from RD to R. This is just very, very general. I mean, we're considering all possible functions here. Of course, what we're going to actually want to do to make this tractable is to restrict it in some way. So the last step is, let's say we consider some class of functions f. How do we select a function from this class? How do we select our f hat? Okay. And of course, as I'm going to mention, we're going to pick some very, very simple answers to these questions in the context of linear regression. But of course, this is like a very, very broad set of questions, and pretty much every machine learning application involves selecting some intricate answer to each of these. But let's now begin with this simple framework of linear regression and how do we actually answer these questions in this context. Okay. So in the context of linear regression, the first thing that we're going to do is we're going to answer question 1 by measuring model performance with the mean squared error. This is with the mean squared error. So people also call this the square loss. I'm going to actually just denote it MSE because this is what you'll probably see in any machine learning library. It'll be called the MSE loss. So what is this loss actually? It's a very intuitive thing. I'll write it as definition 1. So if you're given 2 samples, let's say you're given 2 sets of labels. One is my prediction y hat, and the other is the ground truth y. And let's say these are actually now multi-class vectors and some RC. The mean squared error between y and y hat is given by one half y hat minus y norm squared. And I'm going to put a 1/2 in front just to make my life easier and get rid of some constants when I start taking derivatives. This is, of course, completely optional. This is just a scaling factor, and the error is really dominated by this term. Okay, so why did we want to choose this as our loss function? Well, let me just write it out quickly in 1D. So if my y hat and y are real values, so in 1D, this thing looks like 1/2 y hat minus y squared. And the reason we care about having something like a square here is just so that if you predict some value that's higher or lower, you still get penalized kind of the same amount. And one reason for the square is that you can actually take derivatives of this thing everywhere. It's a smooth function to work with for now. Okay. So that tells us for now how we're actually measuring error on this data. And visually, I'll show how this looks when we actually do a line of best fit empirically in a little bit. But for now, let's move on to the second question. How do we actually select some class of functions to work with? Right now, we're going to pick a very, very simple class of functions. That's just the set of all linear functions from RD to R. So I'm considering this space, and I'm just going to take f such that f of x is wx for some w belongs to R 1 by. I think most people use this w transpose x, but I'm going to stick with the wx for now because when you have multi-class problems, this thing will be a matrix, and it kind of follows the neural network nomenclature here. Okay, so we're just going to consider this simple linear class of functions. And now the question is, given this class of functions, how do we actually learn some f hat from this class? And how do we pick that so that we get some reasonable error on our test data? Okay. So to choose an f hat from this f, what we're going to do is work with something called the empirical risk minimization framework. Empirical risk minimization, or ERM framework. Okay, and all this is kind of saying is at a high level, we're going to find a W that minimizes this mean squared error on our training data. And there's a rich set of theory on why this is probably a good thing to do. And I'm going to refer to those texts in the lecture notes. And I encourage you to look at them if this is a field that you want to get into. And learning theory is a huge, huge field in machine learning. So a very rich area to work in. For now, what this means for us concretely is we're going to find a W that minimizes the following loss. Minimizes this curly L of W, which is just going to be our loss on the training data. So in our regression framework, we're always just going to consider these xi, yi pairs where yi's are real values, so they're in R. So just to make sure this whole thing makes sense, here we have W, which is a R1 by D vector. This x, xi, is an RD vector. Yi is a scalar. And so everything should match up. You'll be predicting a scalar value, and you want to estimate the error against a scalar value, which is exactly this mean squared error. Okay. So the question then is, if we have this loss function, how are we actually going to minimize this loss? And how are we going to pick a W hat that minimizes this loss? So let me write that down here. So how to find W hat that minimizes loss. Okay, so this is where we're going to come to our first and probably the most important learning algorithm in the past decade, which is gradient descent. Of course, gradient descent has been around very, very, very long time. It's just somehow been surprisingly useful in the past decade, especially in the context of deep networks. This is going to be our definition 2, gradient descent. Okay. So given this loss function from RD to R, or some set of parameters P, let's say, to R, and an initial value W naught, and a learning rate, eta, which is greater than 0, gradient descent is used to minimize loss L by iteratively computing the following update rule. So it's going to be W at t plus 1 equals W at t minus this learning rate times the gradient of the loss at time t. And the gradient, of course, is with respect to the W, but this is the only parameter we're working with for now. And to make this a little more concrete, in general, you can do this for any set of parameters, but here we're actually considering these w's in the linear case, so I'll keep this p as a 1 by d. Okay? And this, of course, runs for all positive integers t. So this I'm going to just run. I'm going to let t equal, 1, 2, 3, 0, 0, 1, 2, 3. So, okay. So this might seem a little complicated at first if you have not seen gradient descent before, but let's actually go through a simple example of what this is doing. And this is just, let's say I have the function f of x equals, actually let's call it L of x equals x squared. Okay, so just kind of like my square loss, but it's just a parabola, and of course it has a unique minimum at 0. And so now the question is, if I start at some random point, let's say I start at the point x equals 1, and this is x, and this is L of x here on the axes. What learning rate should I choose? And will I actually recover the point x equals 0 if I keep iterating this process? And how does gradient descent actually look in this case? Okay. Let me just put a dashed line here so things don't get too confusing. So if I just look at L of x here, I'm working with a function from R1 to R1. So the gradient is just the derivative. So I have L prime of x is just 2x. So now what does my gradient descent update rule look like? Let's say I start from some x0. This is my initial condition. I'm going to call it my initialization. And let's say for now, x0 starts at 1. Then I'm going to have x at time t plus 1 is x at time t minus some learning rate eta times my derivative, which I just simplify out as 2 times x of t. Okay, now I can simplify this a bit further. I just take out x of t. I'm left with eta times 2. Okay. So now here's the trick. So if I take eta, for example, let's say, let us pick 0 less than eta less than 1/2. In fact, you can make it 3/2, but let's just stick with 1/2 for now. So what happens? Well, if I write out my update rule, it's going to be x of t plus 1 is x of t times a constant c, where c is less than 1. Okay. So what happens if I take, okay. Sorry, yeah, so if eta is less than 1, I think t should be okay, but we're going to stick with this 1/2 for now. So what happens when I repeatedly multiply a number by a constant c less than 1? Of course, when I do that repeatedly, that process is going to go to 0. So in particular, I have x at 1 is going to be c x at 0. X at 2 is c squared, x at 0, and so on. We'll have x at t is just c to the t times x at 0. But of course, if I look at c to the t, so think about c being a number less than 1, even if c is 0.9, let's say c is 0.9, c power t is going to be a number very, very less than 1. And as t goes to infinity, c power t is going to be 0. So what that means is as I iterate this equation, regardless of which x naught I start from, whether it be x equals 1, x naught equals 1, or x naught equals 2, my iterates are always going to converge. I'm going to keep stepping down in this direction and eventually hit the point x equals 0 as I take infinitely many steps. And so I'm actually recovering the minimum of this quadratic function just by doing this very simple process. And one nice thing about this problem that I've done here, this quadratic, that it's a convex optimization problem. What that means is that there's some unique minimum solution here, and that gradient descent with a sufficiently small step size will always converge to this thing. And we also showed that this convergence is pretty fast. You have this exponential type convergence. You have this factor c to the t in front. So it's converging pretty fast to this solution. So this was a kind of simple analysis you could do for real valued functions. Of course, we took into account that we knew what this loss function was here, and we explicitly computed these derivatives. Now we're just going to do the same thing for linear regression in high dimensions. And the cool part is that we can explicitly write out the solution that we're converging to. Okay, so let's make that our first theorem of the course. So theorem 1. So remember, we're working on a data set. So let me just write out. You have this data set, xi, yi. These are our pairs, I equals 1 to n. This is the subset Rd by n. This is a subset in Rd cross R. And in fact, let's also use the following simplifying notation. I'm going to let x equals the giant concatenation of our n training samples. And I'm going to let y be the concatenation of our n labels. So this x, this thing belongs to R d by n. And this one here belongs to R 1 by n. Okay. So now the theorem is gradient descent with initialization W naught equals 0 used to minimize L of W, which is just summation I equals 1 to n, yi minus wxi squared. This gradient descent algorithm is going to converge to the Moore-Penrose pseudo-inverse solution to this data, if and only if this eta term, this learning rate, is in this interval, 0, 2 over sigma 1 squared, where sigma 1 is the top singular value of x. Okay. So there's a lot to unpack here, but what we've done is we're saying, you give me a linear model. We want to fit this linear model to data. One way we're going to do it is just use gradient descent initialized from 0, and we're going to pick a specific learning rate. We're going to pick a learning rate that satisfies some range. And gradient descent is going to converge to this solution given by the Moore-Penrose pseudo-inverse. And in fact, there's a lot of properties of the solution that are quite nice. It's the minimum L2 norm solution for this task. That's something that will appear in problem set 1. But basically, it's telling you get a very simple algorithm that converges to a good solution or a convenient solution for linear regression. And the fact is we can do this analysis very cleanly, very thoroughly. This is not the case for other non-convex optimization problems. There's no theorem really like this for neural networks that's as clean and telling us what solution we converge to. So it's quite convenient we can do it here. Okay, so the proof is going to go pretty much exactly as we did for the simple case in 1 dimension. It's just there's a lot more bookkeeping to keep track of with a lot of variables. So let's do this a bit carefully. And so let's work through this proof as if we had no idea what to do. We're just going to take the steps that we can take at this point, given the knowledge that we have. So what do we know? Well, let's write out the definition of gradient descent. We're going to have to compute the gradient of our loss function, so we can at least make progress doing that. So one thing I'm going to do first to make life a bit more convenient is I'm actually going to rewrite the loss. Right now we've written it in the standard way in terms of scalars, xi and yi, but I want to write it in terms of these big block matrices x and y. And one thing you should check on your own is that the loss function above is actually equivalent to this. So whatever I had written before, I equals 1 to n, yi minus wxi. This loss function on the right is actually equal to this 1/2 norm of wx minus y. And here x is this big matrix d by n, so wx is just a 1 by n vector. This is also a 1 by n vector. So we're taking this L2 norm of these two vectors. Okay. So now how do we compute gradient of this? Actually, I believe all of you who did the problem set 0 on preliminaries have already done this computation. So the gradient here is actually just going to be wx minus y times x transpose. Oops. Actually, I'm going to write it in terms of y minus wx times x transpose here. And I'm going to do that to make my life a bit more convenient for the analysis later on. Okay. So now what can we do? We can write the gradient descent update rule. So what does that look like? So this GD update rule. In general, remember it was w at time t plus 1 is w at time t minus your learning rate times the gradient at time t. So let's just substitute that in. So now what we're going to get is w at time t plus 1 is w at time t. The two negatives are going to cancel out. I'm going to get a plus eta y minus wt x transpose. Okay. So now to give myself a bit more room, let's copy this over to the next slide. Great. So now keep in mind, we have this initial condition, w at 0. Oops. Here. So we have w at 0 equals 0. So let's just start writing out the terms w1, w2, w3, and so on, and let's see if a pattern emerges. And so first of all, one thing I'm going to want to do is actually rearrange this term up front. I'm going to group the two wt's together. When I do this, I get a wt minus the identity matrix, eta x transpose, plus eta yx transpose. Okay, so all I've done is just regroup the terms in that equation. And I've grouped all the wt's together because this will make my life a bit easier. So now I have w0 is 0. That's my initial condition. This was given in the theorem. So what is w1? Well, it looks to be some complicated thing, but it's just going to be, if I plug in here, w at 0 is 0. So I'm going to get 0 plus eta y x transpose is just eta y x transpose. Okay, what about w1 or w2? I plug this back in. I get eta y x transpose times I minus eta x transpose plus eta y x transpose. Okay. Now what about w3? I don't really see a pattern happening here so far. Let's keep going. So I'm going to take this whole thing here and plug it in up here. So I'm getting eta yx transpose I minus eta x transpose plus eta yx transpose. That's my w2. then I have eta I minus eta x transpose and eta y x transpose. Okay, so maybe I'm starting to see some things happening here now. Let me just expand this. So I have eta y x transpose. I'm just doing expansion. I'm foiling via the first term here. So just expanding everything out, I start to see some kind of pattern emerging. So you see I have this matrix. Let's call this matrix A. See, I have a matrix A squared here, and then let's call this matrix B. So if I do that, I end up getting W3 is B times A squared plus A plus I. Okay. And now if I look back, I actually see that W2 is B times A plus I, and then W1 is just B times I. So now I'm starting to see a pretty clear pattern, and I encourage those of you who are familiar with induction to try to prove this inductively. But what we'll actually see is that WT, let's call it WT. Yeah, let's just look at the term WT. This is just going to be this matrix B times I plus A squared all the way up through A power T minus 1. Now this is good. This looks like some geometric series. And the only issue though is that these A's are matrices. So it's a little tricky to just directly go ahead and do the standard geometric series trick. But let's actually think about what we can do at this point. So let's just expand out what this looks like. So if I substitute my values back for B and A, this looks like eta yx transpose times I plus I minus eta xx transpose, I minus eta xx transpose squared, and so on, up to I minus eta xx transpose to the T minus 1. Okay. So now here's the big trick that we're going to use, and this is where all that material on eigen decomposition and singular value decomposition comes in handy. Because you see here, we have this matrix X. We know in the theorem, if we go back to the theorem statement, at some point, we're going to start wanting to use the singular values of X. So let's start substituting in the singular value decomposition for X. So let's say X equals U sigma V transpose. Then I think in the first introductory math review, we actually did this computation, but XX transpose is a nice matrix, which I'm going to call U. I'm going to call this sigma squared in some way. You have to keep in mind sigma is not necessarily a rectangular matrix, but this, when I do this computation XX transpose, the matrix in the middle will be a square matrix. And in fact, it'll be a, let's write it out. So this will be a D by D matrix. This will be a D by N. And this is an N by N. So this thing here better be a D by D matrix. And sigma squared, what it's going to look like is a D by D matrix that looks like sigma 1 squared, sigma 2 squared, up to sigma D squared. Okay. Okay. So now let's actually work with this and plug this in and see what happens. And I'm realizing I'm running out of room on this page. So let's just copy over this part to the next page. Okay. Great. All right. So another useful trick to remember is that the matrix I, because of the singular value decomposition, the U is an orthogonal matrix, and U transpose is just the identity. So I am going to write as U transpose. So now I'm going to take these two quantities. Oops. I'm going to take this quantity here and this quantity here, and I'm going to substitute it into my big equation up here. Great. So I'm going to have WT is eta y x transpose, UU transpose, identity minus eta XX transpose. This thing is going to be U, the identity minus eta sigma squared, U transpose. And similarly, because we know the power of matrices in terms of this eigen decomposition just commutes with the eigenvalues in the middle, this is going to be all the way up to U I minus eta sigma squared to the T minus 1 U transpose. Okay. Now we can pull out. We have a U and a U transpose everywhere. We're just going to pull these out of this inner expression. I'm going to have a U identity minus eta sigma squared, identity minus eta sigma squared to the T minus 1, U transpose. Okay. Now this is good. And the reason that this is good is because all these things here are diagonal matrices. And so we can actually just look at individual elements of this. So how does this actually look? So let's just say I look at the top row. So I have here a 1. So the identity matrix is going to be a 1, 1, 1 D times. This one here is going to be 1 minus eta sigma 1 squared, 1 minus eta sigma 2 squared, so on. And then all the way to this one, which is 1 minus eta sigma 1 squared to the T minus 1, 1 minus eta sigma 2 squared to the T minus 1, so on. Okay. So now, when I take the sum of these diagonal matrices, I'm just actually summing up individual terms in a geometric series. So what does that look like? If I actually look up the sum of the terms, 1 minus eta sigma I squared, 1 minus eta sigma I squared, and so on. 1 minus eta sigma 1 squared to the T minus 1. Well, this looks like 1. If I'm calling this R, this is going to be 1 plus R squared, 1 minus R to the T minus 1. This is just 1 minus R to the T over 1 minus R. And if I substitute back in, what is this R? This is just 1 minus eta sigma I squared to the T by 1 minus 1 eta I squared. And then this is just 1 minus eta sigma I squared to the T by eta sigma I squared. Great. So what does this mean? Let's copy some terms over. Okay. So this means that WT I can rewrite as a big matrix. So I pulled out this U. I have a big matrix of just these sums. So I have 1 minus eta sigma 1 squared to the T by eta sigma 1 squared. And I'm going to give myself a little more room to write this. 1 minus eta sigma 2 squared to the T by eta sigma 2 squared, and so on. 1 minus eta sigma d squared to the T, eta sigma d squared. And I am leaving out a small subtlety here. Some of these sigma i's, remember they're non-negative. So some of them can be 0. And in fact, if some of them are 0, you'll have to handle the sum carefully. I'm going to leave it as an exercise to the reader on how you do this. It's actually not too difficult though, because what we'll see is when we expand with the singular value decomposition for x, all those terms that would be non-zero will be killed off. So they'll all be multiplied by 0. But okay, let's just assume we have these sigma 1 to sigma d non-zero values for now. Then we've now somehow conveniently simplified the whole expression. But now we're going to think about this limit as t goes to infinity. So when does this thing actually converge as t goes to infinity? So let's just look at one of these values. And let's just look at the numerator, because that's exactly where the t is involved. So we want this thing to converge. Well, we know sigma 1 is the largest singular value. And what happens here for any sigma I is if I take eta, 0 less than eta, less than 1 over sigma I squared, just like we saw in the case for L of x equals x squared, where we took eta less than 1/2, this quantity on over here is going to be less than 1. But we know that because sigma 1 is the largest singular value, we know that if we just take 0 less than eta less than, this should be a 2 over sigma 1 squared, this is going to already give us the smallest range of possible learning rates for which all of the sigma i's, all of these terms, for all I converge. And what do they converge to? Well, because this 1 minus eta sigma I squared is less than 1, I'm taking a number less than 1 power t for very large t. That thing is going to go to 0. And so we'll be just left with 1 here. So formally, what do we have? So if we take 0 less than eta less than 2 over sigma 1 squared, we'll have 1 minus limit as t goes to infinity, 1 minus sigma I squared power t equals 1. And so this is quite nice. So we've canceled out now a lot of stuff. What's going to happen then is my WT is going to be this eta y x transpose u 1 over eta sigma 1 squared. I should write this as a limit as t goes to infinity. Sigma 1 squared, 1 over eta sigma 2 squared, and so on, eta sigma d squared, u transpose. Okay. So now a couple of things that we can do. We see that there's an eta here, here, a 1 over eta. Oops, forgot the 1 over here. And there's an eta up here. So these 1 over etas and etas are just going to cancel. So let me just do that by erasing. Okay. Now we're pretty close to what we want. So let's just substitute in for x. We're going to substitute in its singular value decomposition. So keep in mind, this is this v, sigma transpose, u transpose, u. We have now this matrix 1 over sigma 1 squared, 1 over sigma d squared, u transpose. These two terms are going to cancel each other and become the identity. Now the thing is, what does sigma transpose look like? Well, this, remember, looks like a matrix, sigma 1 to sigma d, and then a bunch of zeros. And this is going to be a n by d matrix. Okay. Now, if I just simplify this, what I end up getting is I get y, v. Now this sigma transpose times this matrix here, you can just see it leaves 1 over sigma 1, 1 over sigma 2, up to 1 over sigma d along the diagonal. So it's going to be another n by d matrix, which just looks like this. And actually from the first lecture, you'll recall that this is exactly y, x, dagger. And that's the end of the proof. So I know this was a very long and involved computation. So I encourage all of you to go through the argument carefully in the lecture notes, and also take time and pause and repeat any of these steps. There's also a problem in the second problem set that walks through this in a little more general setting where W naught is not 0, but rather some random vector or arbitrary vector, and you'll see what solution you get to. But I encourage everyone to try out that problem because I've broken it down into steps, and hopefully it will help you really solidify an understanding of this analysis. But maybe the thing here at this point is to explain why is this analysis so useful. So in particular, a lot of the steps of this analysis we're actually going to use in the foundations of kernel regression, which is going to happen in the next lecture. But more importantly, it kind of gives us some insight into the behavior of linear regression in several settings. And I want to review some of those settings right now. So in particular, what have we just shown? So we showed that gradient descent, so we just showed that gradient descent with initialization and appropriate learning rate recovers the minimum norm solution y w hat equals y x depth. And so what does this actually mean in different contexts? So let's first of all make sure that this means what we think it means in simple settings where n equals d. So let's consider 3 regimes. So the first regime, I'm going to call it the sufficiently parameterized regime. And this is where n equals d. So the number of samples I'm working with is exactly equal to the dimension of the data. Okay. So in this sufficiently parameterized regime, what are we actually trying to do? We're trying to minimize a loss that looks like this. But of course, when you have n equals d, this is exactly equivalent to solving a system of equations that looks like this. And keep in mind now, because n equals d, this is just an Rn by n matrix. And I'm going to assume this matrix is invertible. And if it is invertible, then it's easy to find a solution. I just do what I did in algebra, in linear algebra. And that's just take the matrix inverse, and I get w hat equals y x inverse. Great. And we know actually from the properties of the pseudo inverse and from lecture 1 that x dagger is exactly x inverse when n equals d and the matrix is invertible. Great. So things check out. I'll write this as a check here. Of course, it would be kind of a waste of time to have done this whole thing if it did not generalize to the case where n is not equal to d. But here we'll also see that good things happen. So let's now consider the classical regime, which is this underparameterized regime. And this is where n is much bigger than d. What does this mean? This means that the number of features you have in your data is way less than the number of samples. And maybe for the case of housing price prediction, this is actually kind of a reasonable regime. Maybe you're only considering a classical setting where you have like 3 features, number of bedrooms, number of bathrooms, square footage, but you have 100 samples. So you have way more samples than features. How would you actually solve this problem? Well, there's a nice way to do it, which is that you know that XX transpose. Now this is a D by N matrix. X is a D by N matrix. XX transpose is a D by D matrix. Because N is much bigger than D, we can assume that it's very likely that XX transpose is invertible. So D is less than N. Assume XX transpose invertible. Okay. In this case, what we can do is we can actually use some calculus from like elementary calc 1 or calc 2 to figure out what a solution is. And so we want to find a minimum of some function. How do you find a minimum? You know the gradient has to be 0 at this minimum. So what you would do is just compute the gradient of the loss, which we wrote down before was just negative y minus w x transpose. We just set this equal to 0. And now we just solve for w. So we have w x transpose equals y x transpose. And now x transpose we assume goes invertible. So we get x transpose inverse. And now if you try substituting in the singular value decomposition, you'll exactly see that this is wx dagger. Okay, so we're good in this case as well when n is bigger than d. You're under parameterized. All right. And again, this analysis was probably way simpler than what we did, but here's the cool part. When you're over parameterized, when d is bigger than n, in fact, much bigger than n, this technique still works, although it's not so easy to see how to get a solution from all of the other methods that we just did above in 1 and 2. So here's the issue with the over-parameterized regime. So right now, we said we had to pick a w not equal to 0. The thing is, if we look at this system when we're over-parameterized, we can again write out a system like this. So we have d variables and n equations, but d is bigger than n. And in linear algebra, this means that there's infinitely many solutions to this problem. What we've actually shown is that if we initialize this w not equal to 0, it gives us the solution yx dagger, which is this minimum norm solution given by the pseudo-inverse. So this is kind of a non-trivial thing in this space because there's infinitely many solutions. In the problem set, if you initialize w naught to be another vector, gradient descent will converge to another solution, which can be decomposed in terms of the minimum norm solution and an orthogonal component. But everything is also made explicit, so we can exactly figure out what solution we converge to. And what does this exactly look like as a picture? So right now, what we've shown is there are infinitely many solutions, but GD with W naught equals 0 picks W hat Y X dagger. Okay. And what does it mean when there's infinitely many solutions? Let me just draw out a quick picture here. So let's say I'm looking here on my z-axis is a loss. And let's just say I have two parameters, W1 and W2. So my loss is going to be some kind of convex looking function. And there's going to be a whole slew of values here where the loss here is 0 because there's infinitely many solutions. What did we just show? We showed that if you pick W1 and W2 equal to 0, you're converging to some solution here on this path, which is given by the pseudo-inverse. So here you'll get your YX dagger. If you initialize elsewhere, well, let's say I initialize my W1 and W2 in a different position. Maybe I start out with an initial weird value for the loss. I guess I should point out that the loss is not 0 at 0. Maybe I'll pick a different and start somewhere up here. You'll converge to a different point on this region here. So you're converging to different solutions based on where you initialized. And this analysis that we just did with gradient descent tells you exactly what is that path. So it's quite nice that we have this. Okay. So now that we've done kind of an abstract theoretical view and fully characterized actually how do you solve linear regression, maybe we'll go over some tricks for what does this look like in practice and why is it so simple and easy to use. So even though the theoretical analysis is quite tricky, I mean, at least it was a little bit involved with some linear algebra, The algorithm itself is really simple to code up and use, just based off the result. And this is kind of a theme of the class where the analysis might look a little daunting or intimidating at first, but at its core, the algorithm is just very easy and simple to use and requires only a few lines of code. So let's talk a little bit about how you would do this. And I'm going to call this empirical. Let's call it empirical demonstration. And I highly encourage you to look at the notes in this section to see exactly what linear regression is doing and to get some intuition around this. Of course, the first problem set will require you to code linear regression. I believe it's an optional problem, but I encourage everyone to go ahead and try it out because it should take like 10 minutes to do. So, okay. So what are we given in practice? So in practice, we are given this big matrix X, which of course, remember, is an R d by n, and this vector Y, which is an R 1 by n. And now let's say we want to solve linear regression. How do we do this? To solve linear regression, we compute W hat equals Y X dagger. Okay, and how would you actually do this on the computer? Well, conveniently, you have a lot of libraries out there to help you. One of them is the NumPy library. And NumPy has actually a function for the pseudo-inverse called pin. And so all you do is you set your vector W is Y times pin of X. And that's it. So you've solved linear regression. If you want to predict on a new data point, what do you do? So this is solving linear regression. Now, so for prediction, so if you're given a new point X in RD, you just compute W hat X. And that's it. That's effectively the code for running linear regression on the computer. Of course, there's a lot of tricks to make things more efficient. So if you know that X is a square matrix, you should never actually use this P inverse function. You should use the solve function. So when n equals D, use the NumPy solve function. And the time difference for this is actually shown on this problem set 0, I believe. So I hope everyone has done that and seen that there's a significant difference in this case. Okay. So that's basically it for how to run linear regression. And this is kind of one of the benefits of this course, is that unlike neural networks and all of these other complicated algorithms, the code will always be kind of this simple. So you'll only ever have to run a few lines. Most of the time you can do it on the CPU. You don't need a GPU. And the cool part is that even though linear regression, it's still a simple class of linear models. It's a decent baseline, but we'll see that a simple extension to this will actually start giving us some remarkable results in practice. And this is where we're going to turn to kernel regression in the next lecture. Okay, before I conclude the lecture, I actually just did want to draw, I know it might be a bit simple, but I want to draw the figure for what it looks like when you actually do a line of best fit to data. And this I'm just going to do by hand. I have a code to do this in the lecture notes. And you can actually see the picture of linear regression working. But just at a high level, what does this look like? So let's say I'm given some data points. I'm just thinking of, I have one feature X, and I'm trying to predict one value Y. And here, let's say I think about it as like square footage of a house. And I just want to use that, and I want to predict house price. Okay. So maybe I have some data that looks like this. And I want to be able to fit a line of best fit to this data. So what is linear regression actually going to do? Well, here, it's always going to pass through the point 0, 0, because if we're doing f hat of x equals wx, when x is 0, it better predict 0, regardless of what w has. Okay, so we know that 0, 0 is on here. Now, what linear regression is going to do is keep in mind that it's minimizing the sum of squared error to the data points. So it's going to try to fit a line like this, where it's minimizing these errors shown in red. So it's minimizing the square of these distances. And so we get a line that kind of minimizes that residual. So these terms here in red, these are often called residuals. Okay. So at a high level, this is what you're getting from linear regression. So that's all for linear regression at this point. I encourage you, actually, if you wanted to try this in the case of three-dimensional, and to make a three-dimensional plot of linear regression, you can add in an extra feature x1, x2, and then predict a value y, and see that you get a plane of best fit. Okay, so right now we've established a very simple class of method. We've analyzed it very thoroughly. What we're going to do in the next lecture is move to a class of nonlinear methods that still kind of rely on using a line of best fit, but just first transforming the data in a nonlinear way. And this is going to be kernel regression. And kernel regression is basically the main tool that we will use in the rest of this course. And the trick will be, how do we figure out kernels that give good performance on real data sets? And that's where we'll turn to the neural tangent kernel eventually. But thank you for joining me for this lecture. I hope you all enjoyed it, and I look forward to seeing you in the next one.